Hi everybody, welcome to Physics 30, Unit 2, Forces and Fields. This is a fairly large unit, so we've separated it into two sections. So Section 1 is Electric Forces and Fields. That covers chapters 10 and 11 in your textbook. Section 2 is Magnetic Forces and Fields, and that's chapter 12. So in this section, here below you can see we've separated out into curricular outcomes for chapter 10 and chapter 11. In the interest of time, I will let you read over these curriculum outcomes yourself. Okay, and it's just an idea of kind of what's going on in this chapter. So please feel free to pause the video and read through those. Otherwise, here down at the bottom, the focus of Unit 2 is electric and magnetic forces and fields. Okay, Section 1 covers electrics and Section 2 covers magnetics. Conservation of different quantities is one of the most important principles in science, so it should come as no surprise that this is a recurrent theme in many of the units studied in Physics 30. First, or last unit, you had conservation of momentum, and now in Unit 2 we're going to have conservation of charge. Okay, so here's a checklist for all the things that you're going to be doing in Section 1 of Unit 2. So you have a pre-assessment. Hopefully you've done that already. Okay, and then there are 5 parts, 5 videos. Okay, this first video is electrical interactions. Okay, it's a lot of theory, and you're going to have to apply this theory, but there's notes in practice. There's some questions out of a textbook, and I have a 30-question kind of multiple choice sheet that I'm going to post on the workspace for you to look at and work through. It just kind of cements some of the ideas. Then we have Coulomb's law, forces and fields, electric field lines, electrical interactions. Okay, and then, of course, as always, after you've done the 5 videos and the practice for them, then we'll have a formative assessment, so that's the one that's not for marks. Then we'll have a curriculum review, which is kind of like the unit or the section assignment, so that is for marks. And then you'll have a electric forces and fields quiz. Okay, remember there's 2 sections to this unit, so the unit exam will cover both of those sections, so that'll be written at the end of section number 2. All right, part 1, electrical interactions. As I kind of mentioned before, this one is a lot of theory, it's a lot of pages in the notes. This is going to be a fairly long video, so feel free to pause it at any point. It's all good, everyone. Okay, so part 1, electrical interactions. So try to imagine a time before electricity was even named. Okay, people had noticed interesting effects in certain situations that almost seemed magical or mystic. Okay, the Greek philosopher Thales, okay, and he lived 624 to 546 BCE, okay, recorded that when he rubbed amber, now remember amber is kind of like that hard fossilized tree sap from like Jurassic Park, okay, when he rubbed that stuff, it would attract small pieces of straw or thread, okay, and this effect was called electricity after the Greek word for amber, which just happened to be electron. Okay, the ancient Greeks observed 2 important properties of electricity. Charged objects could either attract or repel each other. These contrasting interactions suggested that there must be 2 different types of charge. Okay, and also repulsion occurred when 2 similarly charged objects were placed near each other. Okay, and attraction occurred when 2 oppositely charged objects were placed near each other. Okay, so these observations can be summarized as the law of charges. Okay, so like charges repel and unlike charges attract. So this isn't anything new. Okay, you've learned this in other courses and just from life experience. Okay, now there was very little progress in the understanding of electricity until the 1600s, when the English scientist William Gilbert, okay, so 1544 to 1603, performed extensive investigations on the subject. He published his book called De Magnet. He compared the effects of electricity and magnetism. He concluded several things, but some more pertinent ones here. Okay, objects only exhibit electrical effects when recently rubbed. Okay, and the effects wear off. Okay, however, magnetic objects don't need to be rubbed. Electrified objects can attract small pieces of many types of objects: paper, straw, thread, okay, all sorts of things, whereas magnetic objects only attract a few types of objects. Okay, and then the third thing, electrified objects attract objects toward one central region, whereas magnetic objects appeared to have two poles. Now, you guys have played with magnets, you know there's a north and a south pole, okay, but remember back when Gilbert published this book, like these were all really, really new concepts. All right, so let's flip the page. Okay, although Gilbert was able to describe certain effects of electricity, he still really didn't know the origin of the electric charges. Okay, so in the 1700s, the American scientist and inventor Benjamin Franklin, okay, attempted to prove that lightning in the sky was the same electricity as the spark observed when you shuffle across the carpeted floor and then touch the metal doorknob. Okay, it gives you that little zap. So he was trying to prove that electricity was that lightning was the same as the door spark. Okay, he performed his famous kite experiment to explore whether lightning was a form of electricity, and luckily he didn't get himself killed, but instead succeeded in drawing electricity from the clouds. He observed that lightning behaves the same way that electricity produced in the laboratory does. Through further investigations, he identified and named the two types of electric charges as positive and negative charges. It soon became apparent that electricity was in everything. Okay, this idea caught the imagination of many different people. Scientists studied electricity's intriguing effects, and entrepreneurs exploited it. Magicians and carnivals often featured the mysterious effects of electricity. Come see us. Woo! Awesome. Okay, studies to determine the nature of electricity continued. These studies were the beginning of the science of electrostatics, which is the study of electric charges at rest. It involves electric charges, the forces acting on them, and their behavior in substances. All right, so let's start into the modern theory of electrostatics. So, today's theories of electrostatics and the nature of electricity, or of electric charges, is based on the models of the atom that Ernest Rutherford and Niels Bohr proposed in the early 1900s. In their theories, an atom is composed of two types of charges: positive charged protons in the nucleus, surrounded by negatively charged electrons. Okay, you guys have seen this before in Science 10 and in chemistry and all that. Like, this isn't new. Okay. In nature, atoms have an equal number of electrons and protons, so that each atom is electrically neutral. Okay, again, this is nothing crazy new. Okay, just as some materials are good thermal conductors or insulators, there are also good conductors and insulators of electric charge. Okay, electrical conductivity depends on how tightly the electrons are bound to the nucleus of an atom. Some materials have electrons that are tightly bound to the nucleus and are not free to travel within a substance. These materials, you'll remember, are called insulators. They don't let the electrons roam around. Materials that have electrons in the outermost regions of their atoms, okay, that are free to travel, are called conductors. So insulators don't let their electrons move very easily. Conductors let their outer electrons move very easily. Okay, so the table below shows some examples of good conductors and insulators. So let's think about this for a sec. What kind of substances make good conductors? What about good insulators? What about these things called semiconductors? Okay, and from the table, note that a good conductor can have a conductivity 10 to the 23 times greater than that of a good insulator. Now let's talk about that for a sec. 10 to the 9 is a billion. So 10 to the 9 times 10 to the 9 would be 10 to the 18. So that's a billion billions. Okay, and that's only 18. And then there's 10 to the 5 more. Okay, so that's like a billion billions times 100,000. Like that's crazy talk. It's huge. Okay. Anyways, that's really neither here nor there. But if you have a quick look, so in this particular chart, the best conductor they're saying is silver. Okay, and he's got a conductivity or relative conductivity of 10 to the 8th. Okay, and then we have copper, aluminum, iron, mercury, carbon. So this chart is saying that carbon is still a good conductor. It's just not as good as some of these other ones. Okay, now in this middle range we have these semiconductors, and I'll define them here in a minute. Okay, but that's like germanium, silicon. Okay, and then insulators or wood, glass, rubber. Look at rubber, like 10 to the minus 15. And that's not very good at all. Right? Doesn't, like, holds on to the electrons very, very tightly. So don't let the electrons run around or move around, I guess, because they don't really run. You get the idea. All right. So materials that lie in the middle, okay, between good conductors and good insulators are called semiconductors. Now, funny thing with them, because of their nature, they are good conductors in certain situations and good insulators in other situations. Selenium, for example, is an awesome insulator when it's in the dark, but when you shine light on it, it becomes a really good conductor. Now, because of this, selenium is very useful in the operation of photocopiers. Very cool. Okay, now, in the early 20th century, a new class of materials called superconductors was developed. These conductors have no measurable resistance at very, very low temperatures. So solid mercury was first to exhibit this trait, and it only does this at negative 269 degrees Celsius, like crazy cold. Okay, more recently, it's been demonstrated that some copper alloys, okay, become superconductors at negative 123. Okay, that's still super cold. Okay, now of course the end result, or the end goal, is to develop superconductors that work at room temperature. Okay, we aren't there yet, but this might happen in your lifetime, and you never know, it might even be you that discovers it. And just so you know, if you do discover that, you will be wealthy beyond your wildest dreams. So someone's got to do it, why not you? Anyways, moving on, there's my plug for higher physics. Okay, so from your work in other courses, you know or you've seen that like charges repel, unlike charges attract. So, two electrons, which are both negative, will repel each other. Two protons, which are both positive, will repel each other. Okay, a proton and an electron, on the other hand, those two will attract each other. Okay, now, let's talk about relative placements and stuff. Because it's only the electrons that move in a substance, okay, and you have to remember that protons are stuck in the nucleus, so they don't get to move in the substance at all. They're just kind of locked in there, okay? And remember, too, that electrons always repel each other. That is, they try and get as far away from each other on the surface of a substance. Okay, so in conductors, this happens really easily, so electrons move with relative ease. Okay, on insulators, electrons really aren't that free to move, so it's possible to have a collection of charge on one end of an object. So as you can see on my little pictures here, so a negatively charged metallic object, so metallics are typically conductors, see all these electrons are pretty much equally spaced on the outside of the object. Okay, so on a conductor, the electrons are free to move, and because of how they're moving, they always want to be as far away from each other as they possibly can. Okay, insulators, on the other hand, electrons are forced to stay kind of where they were, so if they get induced on the one end of the glass rod, per se, okay, they don't get to just spread out and move because they're kind of held tightly to where they were, so they're not free to flow, and we end up with kind of a charged, this is like a partially negative charge on that glass rod. All right, moving on. Feel free to pause at any time. Okay, now, electrons will try to get as far away from each other as they possibly can. We sort of discussed this. The result is the minimum amount of repulsive force on each charge. So as you can see, these two electrons right here, they're pretty close together. So they are pushing, remember they repel each other quite strongly. Now this electron and that electron, they're still repelling each other, but they're further apart, so they're not repelling each other as strongly. So this guy on the end actually pushes that middle charge this way, so that they end up with the same repulsive force. Okay, and then of course the middle charge won't move if they have the same force pushing left and pushing right. So the end result, of course, is this diagram C, where all the charges are equally distanced or spaced out the same. Okay. However, so that's on a flat surface, and it's easy to imagine on that flat surface. However, okay, at the pointed part of a convex surface, so convex, remember that's the pointy things, okay, the forces are directed at angles to the surface. Okay, so a smaller component of these forces is parallel or tangential to the surface. Okay, with less repulsion along the surface, the more charge can accumulate closer together. As a rule, the net electrostatic forces on the charges causes the charges to accumulate at the points of irregularly shaped convex or pointy conducting objects. So basically, because of this kind of round pointy part, these two electrons are actually closer together than, say, those two. Okay, and that happens on pointy convex objects. Okay, conversely, the charges will spread out on irregularly shaped concave objects. Okay, concave, of course, is going the other way. Okay, so these objects, and if we kind of go straight, okay, so a negative charge might be there and there, but then they'll spread out more along the surface. Okay, so anyways, it's all good. Now, last little bit I want to talk about with these. Okay, in a hollow conducting object, all the excess electrons are still repelled outward, okay, as shown. However, they distribute evenly only on the outer surface of the conducting object. There is no excess charge on the inner surface of the hollow object, and that happens regardless of what shape the object is. Okay, so there's never any charge in the hollow part or on the inner surfaces. Okay, and I guess that makes sense, because if the electrons are repelling each other, they are going to repel each other to the outside edges. Because if you put them on the inside edges, then they'll still push each other further away. Okay, so I'm always on the outside edges. Perfect. Okay, so there are basically three different methods that can be used to electrically charge both conductors and insulators. Okay, charging by friction, charging by conduction, and charging by induction. Okay, now in order to determine the presence of charge on an object, we use a simple tool called an electroscope. Okay, and there's two basic models. Now, the most common is the metal leaf one, but the tinfoil straw one is still there, so I'll explain both. Okay, so first, the metal leaf electroscope. Okay, basically, okay, when neutral, the leaves hang straight down. But when the electroscope is given a charge, the leaves, because they have the same charge, repel one another. Okay, so first of all, you have this metallic knob and stem. Okay, so that's the knob part up here, the head. Okay, and this stem kind of right here, okay, that's metallic. And then you've got these super light leaves down here at the bottom. Now, it's all metallic. They're all good conductors. Okay, now, you have this insulating rubber stopper, so that makes sure that we don't lose any of our charge to the glass box on the outside. Now, remember, glass is a insulator as it is. Okay, so it's just there to hold and whatnot. Okay, so when we end up with a charge on this electroscope, let's say if we put a negative charge on the leaves of the electroscope will all be negative, so then they spread apart. Now, this also happens when they're positive, but we'll get into that in a little bit. Okay, the same thing happens with this tinfoil straw electroscope. Okay, when it's neutral, the straw, this middle part, hangs straight down. Now, of course, when it's charged, okay, the object, the support column will repel the straw, which pivots here right in the middle. So basically, let's say we give it a whole bunch of electrons, so it's all negative. Okay, so these parts become negative, the straw becomes negative. Okay, and then there's a repulsive force here and a repulsive force there, so that the straw bends the way it does. Okay, Anyway, so two basic styles of electroscopes. Okay, so funny things about electroscopes. Okay, an electroscope's function is to detect the presence of charge. While it's true that the greater the deflection, the greater the charge, right? Like if we have, I'll back up a page. Okay, if the leaves spread out really, really, really far, then that means there's a lot of charge. There's a lot of charge repelling, so the leaves spread even further. Okay, but even though they spread further, we can detect kind of a relative amount of charge. Okay, these devices don't measure the amount of charge present. Like there's no numbers involved. It's just we look at the angles that the leaves spread or that the straw bends, and we say, oh, that's a lot of charge, or that's not very much, but there's no numbers attached to. Okay. Also, these devices don't indicate which type of charge, either positive or negative, the electroscope may have. Okay. However, a charged electroscope will react differently to known positive and negative charges. So with just a little bit of thinking, we can predict which type of charge an electroscope might have. Okay, that's going to require some thinking, and I haven't even taught you that yet, so don't worry, we'll get there. So electroscopes are super handy in our study of charged objects or charging objects. Now, another useful tool are these tiny little spheres called pith balls. A pith ball is made of a very, very light material, okay, and has a conductive coating on the outside. These spheres react with electrically charged objects and help in our understanding of electrostatics. Okay, so we'll look at both of these things here in a minute. So electroscopes and pith balls. Okay, so let's review some of the more important rules and laws of electrostatics. So conservation of charge. Okay, remember, charge can't be created or destroyed, it can only be moved from one place to another. If one object loses 5 electrons to become positive, then those 5 electrons had to go somewhere. So they have to go to another object to make that other object negative. Now remember, to become negative, you gain electrons. Now, positive things don't get to move, so to become positive, you have to lose electrons. To become negative, you have to gain electrons. It's never the positive things that come and go. All right. The law of charges, remember, like charges repel, unlike charges attract. Okay, and now charge is measured in a unit called the coulomb. Okay, the unit for that is a large C, a capital C. Okay, and 1 electron has the charge of negative 1.60 times 10 to the negative 19 coulombs. And 1 proton has a charge of positive 1.60 times 10 to the negative 19 coulombs. Very, very tiny. It's important for you to understand that these things have exactly the same charge. So if they're in an atom, you have the same number of protons as you do electrons. So in an atom, you have an electrically neutral object. In an ion, on the other hand, you either have an excess of electrons or you have a deficit of electrons. Okay, and that's what makes an ion either positive or negative. All right, let's flip the page. Okay, so ways to charge objects. So the first way is called charging by friction. So some substances acquire an electric charge when rubbed with another substance. For example, an ebonite or plastic rod becomes negatively charged when rubbed with fur. We can explain this phenomenon with the help of the model of the electrical structure of matter. An atom holds on to its electrons by the force of electrical attraction to its positively charged nucleus. Some atoms or combinations of atoms exert stronger forces of attraction on their electrons than others. When ebonite and fur are rubbed together, work is done on the electrons. Some of the electrons from the fur are captured by the atoms in the ebonite. The ebonite attracts the electrons in the fur, okay, which exerts stronger forces of attraction on those electrons than do the atoms making up the fur. Thus, after rubbing, the ebonite or the plastic rod gets more electrons, so end up with a negative charge, and the fur having lost some of its electrons, has a deficit of electrons or a positive charge. Remember, both these things are neutral to begin with, but after you rub them, okay, it's the plastic rod that ends up being negative, it's the fur that ends up being positive. Okay. Now, after charging by friction, the rod has gained electrons and is now negative, and the fur has lost an equal amount of electrons and has become positive. Remember, the protons are stuck in the nucleus, okay, so they don't get to move, but the electrons are free to travel between the materials. Notice that the electrons differ in number from A to B, but the protons and the fur, protons on the fur are the same from A to B, as are the protons in the ebonite rod. So if we wanted, we could certainly count. See, in A, they're initially neutral, so it's got 1, 2, 3, 4, 5 protons. Okay. Afterwards, we still have 1, 2, 3, 4, 5 protons. The ebonite has 1, 2, 3, 4, 5, and then after 1, 2, 3, 4, 5. Now remember, there's billions of electrons and protons in these substances. We just draw a small number of them just to kind of show the relative idea of what's going on. The protons stayed the same before, but if you have a look, there's more electrons on the ebonite after, okay, and less electrons on the fur after. See, there's 5 protons still, but there's only 3 electrons. Well, that means this fur ends up with a +2 charge. And then if you have a look, you've got 1, 2, 3, 4, 5, 6, 7 electrons and 5 protons. So that means there's a -2 charge on the ebonite rod. All right, moving on. Okay, the same explanation holds for many other pairs of substances, such as glass and silk. The electrostatic series table below lists many of the substances that can be charged by friction. If 2 substances in the table are rubbed together, the substance that is higher in the table becomes negatively charged, while the other substance becomes positively charged. So for instance, if we have this ebonite rod rubbing with fur, okay, so the ebonite gets to be negative and the fur gets to be positive if those 2 things are rubbing each other. Okay, if we had glass and wool, okay, glass would end up positive, wool would end up negative. Okay, that's just the way it works. Okay, charging objects by friction can also occur during collisions. The collisions of water vapor molecules in rain clouds, for example, cause the separation and transfer of electrons. The result is that the vapor molecules become positively or negatively charged, eventually resulting in lightning. This process of charging objects was also observed by the Voyager spacecraft on its mission to Saturn. Colliding particles in the rings of Saturn create electrical discharges within the rings, similar to lightning on Earth. Wow, there's like lightning on the rings of Saturn. That's crazy. Okay, so let's consider what happens when an object charged this way interacts with an electroscope. Okay, so a simplified neutral electroscope looks like this. Now, just for simplicity, remember there's billions of protons and billions of electrons on this. But if this is neutral, let's say that there's 3 positive charges, okay, and let's put 1 positive charge kind of on that part and 2 down here. Okay, if we're neutral, that's positive, sorry. Okay, so there's also going to be 3 negatives here, and negative on the kind of middle part, and 2 negatives on each of the leaves. So we're electrically neutral, everything's good. Okay, so that's kind of the idea there for a neutral electroscope. So let's talk about when a negatively charged rod comes near but doesn't touch the head of the electroscope. So we've got this negative rod. Okay, so what's going to happen? So let's just make this neutral. Positive, negative, positive, negative. Okay, positive, negative, positive, negative, positive, negative. Okay, So when you bring this negatively charged rod close, what's it going to do to all the electrons in the electroscope? Well, remember, electrons are going to get as far away from each other as they possibly can. So the electrons on the rod are going to push the electrons in the electroscope's head down. So what's going to happen, and I'll just erase this for a sec, or at least the negatives, or try to get the negatives. What's going to happen is that all the negative charges, sorry, there was an extra positive charge, all the negatives are going to get pushed far away from the head of the ebonite rod, the negatively charged rod. And what happens now, you can see that the head has become positive, the leaves have become negative. So what's going to happen to those leaves? Now remember, the negative charges are going to try and get as far away from each other as they can. So what ends up happening is that the leaves spread out. Okay, because the leaves are negative, so what we end up with is an electroscope that looks like this. Okay, because the leaves of the electroscope are negative. Okay, and the head of the electroscope is positive. Okay, now when a positively charged rod comes close, so now positive, so what's that going to do to the electrons? Remember, the protons don't move. So what happens is all the electrons in the whole electroscope, they get attracted to the positive. So you end up with a whole bunch of negative charges up in the head of the electroscope. Now, what that means is that there's no electrons in the leaves anymore, or at least less electrons, okay? And you end up with the leaves of the electroscope being positive. Well, that's going to make the leaves separate still because they're positive. So remember earlier we said that electroscopes are very good at detecting if there's charge present, but remember it doesn't do a very good job of is there a positive rod that's close or a negative rod that's close? Okay, as you can see, the electroscope behaves the same way regardless of the type of charged rod that comes close to it. In this way, electroscopes detect the presence of charge, but can't distinguish the nature of the charged rod. Because all you'll be able to see is the leaves spreading apart. It'll happen that way with positive and negative rods. So, again, very good at detecting the presence of charge, not so good at detecting what kind of charge there is. Okay. The nature of why the leaves separate is called charging by induction. Okay, we're going to talk about that later on. Okay, so just a couple of things to note. The crystal structure of the metals hold the nuclei in place. The positive charges within the nuclei remain where they are, and therefore it is only the electrons that do the moving. An induced charge separation is temporary. When we take these rods, this positive rod, if we took it away, okay, all the electrons would go back and separate out, okay, and the electroscope would return to normal. The leaves would, okay, come back together, and we would end up with our just straight hanging down leaves just like it was before. Okay, let's flip the page. Okay, another example of induced charge separation is when a charged rod is brought near a neutral pith ball. Okay, so remember pith balls are extremely light, okay, and have this conductive coating on the outside. Okay, initially nothing appears to happen, but after a few seconds the pith ball is attracted to the charged rod. So how can a neutral object be attracted to the charged object? To illustrate, suppose a charged rod, in this case a positive rod, is brought close to a pith ball. So essentially the pith ball starts out neutral. Okay, we'll put 2 protons, 2 electrons to make it really easy. Now, if this rod is brought close enough, okay, remember, it's going to attract the negatives. So what's going to happen? The protons don't get to move, okay, but both electrons are going to end up on this outer edge being really attracted to that positive rod. Okay, so what ends up happening, this negative part, okay, is attracted to the rod. And since the negative side of the pith ball is closer to the rod than the positive side, the attractive force between the negative side of the pith ball and the rod is slightly greater than the repulsive force between the positive side of the pith ball and the rod. Okay, the result is a net force towards the rod. So we end up with the pith ball kind of moving towards or being attracted to the positive rod. Crazy. Okay, but that's how a positive charged object can attract a neutral object. We get this charge separation and it attracts. So let's flip the page. The second method of charging is called charging by contact or conduction. Objects can become charged by the transfer of electrons from a charged object to an uncharged object by simply touching the objects together. This process is called charging by conduction. When the objects touch, any charge on the objects redistributes so that all objects end up with the same charge. Mathematically, the charge averages out. This means that we take the sum of the charge on all objects, usually 2, but there can be more, and divide by the number of objects. So, as an example, if a 5 or plus 5.0 coulomb charged object is brought near and touches a negative 3.0 coulomb negatively charged object of equal size, when the charges are separated, what will the charge on each object be? Or what will be the charge? Okay, so what we do, we just go, okay, plus 5.0 coulombs plus negative 3.0 coulombs. And there's 2 objects, so we just divide by 2. Okay, so plus 5 plus negative 3, of course, is positive 2. So plus 2.0 coulombs, and dividing by 2 objects. So that means that each object would get plus 1.0 coulombs. Okay, makes sense? Now, this is an overly simplistic view that works only when the objects are close to the same size. If one sphere is larger than the other, then the larger sphere will receive more of the charge. When the spheres are in contact, the excess charge moves, the excess charges move to become equidistant from each other because of the forces of repulsion between the like charges. Because there is more room on the larger object, there is more room for electrons to spread out, so when separated, the larger object will have a greater portion of the total charge. Now, charging by conduction is similar to charging by friction because there is contact between the 2 objects and some electrons transfer from one object to the other. Okay, electroscopes and pith balls can be charged by conduction to help formalize these concepts. Because the relative size and shape of the charged object is often different than the neutral object, number calculations like the one above aren't really appropriate. However, the nature of the charge after contact, either positive or negative, can still be determined. So just to recap, calculations like this really only work when the 2 objects are pretty close to the same size. Okay, so when you have a rod and a pith ball, okay, clearly not the same size. So the thing is, so even though they won't end up with identical charges, they'll still end up being, we'll still be able to figure out if they're both end up being negative or both end up being positive, that kind of thing. So let's flip the page and have a look. Okay, so for an example, a positively charged rod is brought near and touched to the head of an electroscope, then removed. Make a sketch, including the placement of charges, showing the position of the leaves of the electroscope after this has occurred. Okay, so we have a positive charged rod, okay, and a neutral electroscope. Now these are not the same size, so we don't even have any numbers to figure out an average. But what happens? Okay, this guy is neutral, so he's got positive, negative, negative, positive, positive, negative, positive, negative, that kind of thing. So we've got the same number of positives as we do negatives. Now, when these things touch, what ends up happening, see, this guy is really positive, and this guy is neutral. So what's going to happen is some of the electrons from here are going to jump onto that, trying to balance off the charges. Okay, so what ends up happening is there's not enough negative charges on the electroscope to balance off the positive rod. Okay, so we're not going to be able to make it neutral. So what happens is that both of these objects are going to end up slightly, okay, positive. Okay, so the rod will end up slightly less positive, and of course the electroscope will end up like just positive. So the electrons jump off the electroscope onto the rod. Okay, so really we end up with plus, 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 plus. Okay, so let's say we take, like again, my overly simplistic drawing. So let's take off all 6 of those electrons. Okay, so we still, so this cancels, that cancels, 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 cancels. So we end up with a slightly less positive rod, but now the electroscope, it took all 6 of those electrons off. 4 electrons, because there's 4 protons, sorry. Okay, anyways, it took off all the electrons, so now when you separate them again, okay, so now we have this positive electroscope. Now, of course, because it's positive, the leaves, okay, they are the same charge, and they're free to move, so that ends up being, the leaves end up separating like so. Does that kind of make sense? So they end up separating. Sorry, in my simplistic view here. Okay, there's only 2, but they still separate. We end up with a positive electroscope. Awesome. So again, kind of a simplistic view, but that's the idea. So the next example, a negatively charged plastic rod is brought near and touched to a pith ball, then moved a short distance away. Make a sketch of this scenario after final separation. Include relative charges on the objects and state whether the pith ball is attracted or repelled by the rod. Okay, so here we've got this pith ball, and it is touched by a rod. Okay, so let's see, we've got, it's negatively charged. Okay, and then this guy, plus, plus, minus, minus. Okay, so now, what ends up happening here is, oh, that's negative. So what ends up happening is the electrons they're trying to get really far away from each other on the rod, so some of the electrons actually jump on to the pith ball. Okay, so now when these things separate, okay, this guy is negatively charged. The pith ball, so let's say just 2 jump on, it doesn't matter. Okay, so plus plus, now we've got 1, 2, 3, 4. So now it's negative. Okay, so we end up with a negatively charged pith ball, a slightly less negative rod. Now, what's going to happen when these are separated? These are now equal. They are the same charge. They're both negative, and negative things repel each other. So what's going to end up happening is the negative pith ball is going to get repelled. 3, 4. Okay, and the pith ball will end up moving away. So we end up with these a force or electric force pushing the pith ball away. Okay, it's repelling, and the pith ball ends up with a negative charge. All right, so that's that one. Okay. So before we start the next method of charging, let's talk about this word induction. Well, I have used that already, but let's just define it and go from there. So induction is a process in which charges in a neutral object shift or migrate because of the presence of an external charged object. This temporary charge separation polarizes the neutral object. Okay, one side of the object becomes positively charged and the other side is equally negatively charged. Although the object now behaves as if it's charged, it is still electrically neutral. No electrons have transferred yet. The charging object and the neutral object do not touch each other, so there is no actual transfer of charge. Okay, if a negative, so an example of this, a negatively charged rod is brought near but does not touch a conductor, the electrons on the neutral conductor will repel to the side furthest from the charged rod. The neutral conductor has not gained or lost electrons, but only rearranged the position of the electrons. This is charge migration by induction, as the electrons are able to move freely in the conductor. So if you have a look at this, like say this is a pith ball, okay, so a negatively charged rod is brought near, so all the negative charges go to that side, are repelled by the rod, okay, and so this side ends up being partially, so this is the partially sign, so partially negative. Okay, now it's not that the protons move towards here, because remember the protons are stuck wherever they were before. Okay, they're kind of evenly distributed, but it does make this side partially positive. Okay, so we end up, even though it's still electrically neutral, we end up with a partially negative side on the side away from the negative conductor or negative rod, and we end up with a partially positive side on the side nearest the rod. So ultimately what happens is there is an attractive force between these, because the partially positive side is closer to the rod, even though the ball is electrically neutral still. Okay, a similar process happens on an insulator, just not to the same extent. In an insulator, the electrons are not really free to move, so they just shift slightly relative to the nuclei. This process of charge shift causes the atoms to become polarized, where one side of the atom becomes positive and the other side becomes negative. So even on a conductor, like insulator, like a tiny bit of paper, what ends up happening is, if you can picture an atom, okay, the nucleus is positive, but all the electrons in that atom kind of shift to the other side. So even though we don't get all the negatives kind of over here, like we would in a conductor, we get all the atoms lining up. Okay, so all the protons are on kind of the right-hand side, and all the electrons are kind of on the left-hand side of the atoms, and we still get, even though it's not a charge migration like before, we get a charge shift. Okay, and anyways, the end result is the positive side of the atoms is still attracted to that negative rod, and that's why a negative rod will attract a tiny bit of paper, even though the paper is still classified as an insulator. Okay, in both cases, the distance from the negatively charged rod to the positive end of the neutral object is less than the distance of the negative end of the object. Okay, therefore, the attraction of the opposite charges is greater than the repulsion of like charges, and the net force is attractive. Charge separation by induction, which results in the polarization of objects, explains electrostatic situations such as the initial attraction of a neutral piece of paper to a negatively charged rod without touching. Crazy. Now, just for the fun of it, let's talk. What happens when they do touch? Oh, so initially this little piece of paper is attracted to the rod. Okay, but as soon as it touches the rod, remember, it's neutral, the rod is negative, so we're going to end up with negative charges, okay, going on to the tiny bit of paper. Okay, so all of a sudden now the rod's negative and the tiny piece of paper is going to be negative, and well, if they're both negative, then they're going to repel. So in this induction thing, initially they are attracted to each other, then they touch. Okay, charging by contact, it makes the charges the same, or at least the same nature. Okay, so now they're both negative, and then they're going to repel each other really quick. So initially, they're attracted, they touch, now they're repelled. Awesome. Okay, so we have already seen these results in our discussion of how an electroscope detects the presence of charge. When a charged rod is brought near an electroscope, electrons are either attracted to the rod, so they move to the head, or repelled from the rod and forced to the leaves. Both scenarios cause the leaves of the electroscope to spread out, because the leaves have the same charge. Let's draw some of this. Okay, so if we bring a positive rod close, okay, all the electrons are going to get sucked up into the head, which leaves a net positive charge on the leaves, so they separate. Okay, now again, we haven't touched yet, so this is charging by induction. So we have induced a charge migration on the electroscope. Negatives migrate towards the head. Positives, remember, are stuck where they are. So we end up with a net positive charge on the leaves, so they separate. Okay, when we bring a negatively charged rod, of course, it forces all the negatives further away. Okay, so the net result is the electrons migrate down to the leaves, leaving the head partially positive and the leaves negative. So of course, if both leaves are negative, then they separate and it looks the same. Awesome. So this brings us to charging by induction. In the situation shown above, the electrons in the electroscope return to their original positions when the negatively charged rod is removed. These objects lose their polarity and remain electrically neutral. For conductors, like the electroscopes above, it is possible to maintain a residual charge by adding what's called a grounding step. Grounding involves touching or connecting a wire from the object to the ground. The grounding path is then removed while the source charge is still present, okay, and the grounding step allows the conductor to maintain a charge. Okay, the complete process of charging by induction includes grounding. Okay, the process is illustrated below. So here's the deal. Okay, we end up with, so this is a negatively charged ebonite rod. Okay, now when it's brought close to this pith ball or conductive ball, I guess, okay, it pushes all the electrons away. Now this little symbol, this means a ground. So you either touch it with your finger, that provides a path to the ground, or you can connect a wire to it, it doesn't matter. But what ends up happening, okay, so this allows for a path for the electrons to leave. Okay, so as the electrons, remember, they want to get as far away from each other, and especially that negative ebonite rod. Okay, so getting off the ball, okay, and going to the ground lets them get further away. So now what happens? So you leave this rod here, we end up with the electrons jump ship, okay, and go into the ground, okay. Now, it's important to note that you have to leave the ebonite rod there while this is happening. The electrons jump, okay. Now, if you break the ground, okay, so take the wire away or stop touching it, whatever, okay, now you've made it so that the electrons can't get back on to the ball. Okay, now if you take away the rod, what ends up happening is the electrons that are still left on the ball, and then there's still a few, okay, they just redistribute as far away as they can from each other, but there's less electrons than protons, so you end up with a positively charged object. So that's kind of cool. Now, can grounding produce a negative charge on a neutral object? So let's talk about that. Okay, if we bring a positive rod close to but don't touch, what this does, that induces a negative polarity on this side. It brings the negatives up to, okay, close to the positive charged rod. Now, if we put a ground here, look, there is a net positive side here. Well, that's going to bring electrons up from the ground. Okay, so that more electrons are going to come trying to balance off this kind of positive side or partially positive side. Now, if you cut the ground, so pull away the wire or stop touching it or whatever, now these extra electrons can't get back off. So when you remove the positive rod, what's going to happen, now the electrons are going to go back to normal, or they're going to try and repel each other, okay? But the thing is, there's more negatives now than positives, and you end up with a negatively charged object. Charged. Kind of crazy. So yeah, we can produce a positive or negative charged object by induction. It just includes, or has to include, this grounding step. Awesome. Okay, so as the last part of this, let's talk very briefly about lightning and how lightning gets its charge. Okay, so under the right conditions, the motion in a cloud causes water vapor molecules to collide and transfer electrons. Okay, recall that this is charging by friction. The water molecules rub against each other. Okay, some of them end up with extra electrons, some of them end up with obviously with an electron deficit, making them positive. So as the water vapor cools, they condense into water droplets, which hold on to electrons even more readily than the water vapor. The droplets are heavier than the vapor, so they accumulate on the bottom of the cloud, making the bottom of the cloud negative. So here you can see on the picture, the bottom of the cloud becomes negative, the top of the cloud becomes positive. Okay, the top of the cloud has more positively charged water vapor, making the top of the cloud positive. Now, the bottom of the cloud, being very negative, ionizes the air around the cloud, making a conductive plasma in the air. The extra electrons in the cloud follow this plasma along a zigzag route towards the ground. This is called a step leader. Not a ladder, a step leader. Okay, now the bottom of the cloud, being really negative, induces charge separation within the ground below. This makes the top layer of the ground positive. Okay, so that's here. Top layer is positive because, of course, the electrons in the cloud force the electrons further away. So you end up with this positive on the top of the ground, negative kind of below that. Okay, this the charge separation at the surface also ionizes the air, making a conductive path upwards. When the positive charge begins to move upwards, it's called a streamer. Okay, when a negative step leader meets a positive streamer, and this happens about 100 meters above the surface, now you've made a complete pathway from the bottom of the cloud to the ground, and lightning strikes. Okay, it's crazy. And when lightning strikes, it strikes about 100,000 kilometers per second. It's absolutely insanely fast. So yeah, there's no time to get out of the way of a lightning strike. Of course, that's why we're always so careful around, lightning storms and that kind of thing, because you don't want to be hit by that. That'd be very bad. So anyways, I know this was a really long section, everyone. I'm sorry, there's a lot of theory going on, okay, but I want you to practice this material. Okay, it's in the textbook, section 10.1. It's on starts on page 523. So there's some questions. I've also included a multiple choice kind of worksheet for you to go through and practice on. It's just, like I say, little questions that just kind of cement these ideas. So please try those as well. It's also in the workspace. Thanks for your patience, everyone, and we'll see you next section.